So, in this module we will study about types of damping. How many types of damping are there? So, negative damping is there, material damping, structural damping, radiation damping, and we will discuss about models of damping. So, what is actually damping? What is the meaning of damping? So, just look at this pendulum. So, if I pull this pendulum and leave it, set it free, it will oscillate. So, it will not oscillate forever, it will oscillate for few cycles and then stop. So, like the energy, that is input energy I have given in the form of this displacement, okay, that is getting lost. So, where it is getting lost? It is getting lost in friction between this pointer and my hand. So, this, because of this friction, energy is lost. Like that, any structure which is vibrating, it will ultimately come to rest. So, in small time or in large time, but it will come to rest. So, what is actually happening while coming to rest is vibration energy is getting lost. So, the phenomenon through which this vibration energy gets lost is called damping. So, that means it is reducing kinetic energy. So, that is called damping. So, we will study in detail about damping in this module. So, what are types of damping? Okay. So, damping generally are of three types. One is the damping required to stop the motion, so that we call it as critical damping, and then another one we call it as under critical damping, if damping is less than that required to remove the complete energy from the system, and then over critical damping is like damping which is more than required. This critical damping ratio can be estimated using this formula, that is 2m omega n, where m is mass and omega is natural frequency measured in radians per second, m mass measured in kg. So, this is critical damping. Now, critical damping ratio, that we use this term zeta. So, this is the damping present in the structure. This critical damping is damping required to remove vibrating energy completely from the structure. So, this ratio is called critical damping ratio zeta. So, we have these zeta values can be less than 1, it can be equal to 1, and it can be more than 1. So, that means if zeta value is less than 1, that means damping present in the structure is less than critical damping, and if it is equal to 1, damping present in the structure is equal to critical damping, and damping present in the structure is more than critical damping, that is over critical damping. So, let me show you the example of this under critical, critical and over critical. So, as I told you, this pendulum. So, if I leave this pendulum here, so if it comes back and stops here in that half cycle itself, so then we can call it as damping present in this system is critical damping. So, that means what? Damping present is just required to stop this oscillation and set to static equilibrium position. Okay. But if we provide some damping which is less than the critical damping, what happens is it will come here, it will not stop, it will overshoot. So, overshoot, and that sets oscillation. So, this damping is called under critical damping. And then what is over critical damping? Over critical damping means if I leave it here, it will come and come to rest, but it will take much longer time to come to rest. So, one best application of this over critical damping is recoil mechanisms in guns or door closures. This automatic door closures are there. So, usually when you open the door while entering and then leave it, so door closes slowly. So, if say in that door closure, if under critical damping is there, then before person enters, it will come and hit the person. So, that is why that damping is adjusted such that it should come slowly and then shut down finally. So, that is over critical damping. Now, if you look at this graph, in this one, x axis, this is a time scale, and then you can see the blue line. So, this blue line is when there is no damping present. So, that means when there is no damping present in the system, then the amplitude of the system will never come down. So, same amplitude, this you can see here 1, -1 to +1 is the amplitude. So, -1 and +1 is the amplitude. So, it is not coming down. But when damping is critical, this red line if you can see, it is not doing any oscillatory motion. So, it starts from here and finally comes to rest. somewhere here it is coming to rest. And then when damping is under critical, so that means in one cycle, when it is crossing the zero line, the energy is not removed completely from the system. So that means it overshoots from there, it comes down, and then again it goes back, and again it overshoot, again comes down, again goes back, like that. That is under critical damping case. In case of over critical damping, what it does is it comes to rest, but after much longer time compared to the critical damping. So these are the three types of damping present in the applications. So what applications are there? So usually structural engineering applications, damping is limited to very much less than critical damping only. So these damping values are, like if we look at structure alone, in general cases, structures damping present in the structure is taken as around 2%, structure together with the soil system it is taken as 5%. So especially this is for RC structures, and for steel structures it is taken from 2 to 3%. Then damping, how damping can be estimated? It can be estimated by experiments. Now what is role of damping? So role of damping is removal of kinetic energy from the vibrating system. So as you can see this one, okay, amplitude of vibration is diminishing steadily, and there is a pattern in which this reduces. So these ratios can be fixed. With a fixed ratio it reduces, and that reduction gets converted into heat, waves, and different forms. Now there is negative damping also. So negative damping means what happens is, like when vibrations are small, sometimes it is followed by the damping which is negative. Negative means vibration amplitude increases. So that means it's something like a self-excited. Okay, you can see this one. So vibration is starting in a small range and then suddenly it increases. Okay, most of the time systems unstable. And material damping. So this material damping usually occurs inside the volume of the structure. So in between, it happens in between the friction between the molecules of the structure. So we consider the entire volume to be responsible in that. Okay. So how it is calculated? If a load is applied on a material, so this is a stress strain curve or load deformation curve, you can call it as. So this is elastic energy. So energy stored in the system. So this is area 1 is representing energy stored in the system. Now if you leave it at that place, so it comes back, and then there is some permanent deformation. So the energy which is like the line which is coming back, and if you calculate this energy, so this is the energy which is recovered, that is mechanical energy which is recovered. And the third one is, this is the, like when you are applying to and fro motion or the cyclic load application. So this is called hysteresis, which starts from here. Actually it starts from here, goes here, and then comes back, and so this completes one cycle. So that is energy loss per cycle per unit volume of the material. This is called hysteresis. So that is a measure of actually the damping. And then structural damping. So usually structural damping, so this is in mechanical connections, it occurs between the joints and connections. Usually this will be in the form of friction, and the energy loss is due to heat and waves. And then radiation damping. So if a body is supported on the ground and body is vibrating due to some external forces, so energy is dissipated in two directions. One is in the form of waves which are going to the ground, and also in the form of waves which are interacting with the surrounding atmosphere. So this is called radiation damping. And then damping is present in the fluid systems also. So it occurs in the volume of fluid immediately surrounding the structure. So that is fluid damping. So it is usually in the form of friction between the layers of the water and the body. And let's discuss a bit about linear damping models. So the instantaneous damping force acting on the structure is usually proportional to the instantaneous speed. and it is usually directed opposite to velocity. If you can take this as idealized system, and the equation of motion which is set here, equation of motion. Okay. So, if say response u is harmonic, the combined elastic force and damping force is given as like this: u by ua whole square plus P1 minus u divided by C omega Ka whole square is equal to 1. So, that is representing this equation. Actually, it is representing this elliptical form which is on the shifted axis, translated axis. Okay. So, if we calculate the area of this ellipse, we get pi C omega ua square. So, ua is displacement up to this point, peak displacement point, and viscous damping coefficient is calculated as C is equal to area of the hysteresis loop divided by pi omega ua square. That is how C is calculated. Now, in summary on the types of damping. So, in all structural engineering applications, damping is usually under critical damping. So, critical damping means the damping value which is required to completely remove the energy of vibration, that is critical damping, and damping, if damping is less than that critical damping, it is called under critical damping. If damping is more than the critical damping, that is called over critical damping. So, usually in RC structures, along with the soil, damping is taken as 5%, and in steel structures it is taken as 2% or sometimes 3%. So, there are many other forms of damping: positive damping, negative damping, radiation damping, material damping, and fluid damping. So, for the purpose of structural dynamics, our damping value is usually less than 20% of critical damping. So, that is the zeta value usually less than 0.2.